with Home Lab number 1, or Lab 3 as I think it is on the online submission site, for Physics 2211, Section HP. It's the Constant Velocity Motion Lab, and what I did was I had a large holiday popcorn tin that I rolled down my hall. I videotaped that, and I plotted it in Tracker, and I'm going to go ahead and show you this video. Now where the tin is right here, that you see now, it's already rolling. Nothing's actually touching it. I'm not touching it. I rolled it from off screen, so it already has all of the momentum it's going to have, and here is the video. As you can see, I chose my x-axis to be positive in the left direction so that my graph wouldn't have negatives in it. And that kind of screwed with my model output, the display of the model a little bit, but I'll get to that later. I used the stick, the measure stick here. I took a measurement of the popcorn tin and input it for the stick here. It was, I believe, 0.3125 meters in diameter, and I did the diameter. My video is actually about 3.2 seconds long. I've got a frame rate of about 30 frames per second, which gives me a delta T of about 0.033 every step. For my model, I took as an assumption that the net force would be 0 in all of my Newton's second law calculations, the fundamental momentum calculations. And when I did that in my model, it gave me some predictions for the motion of the tin, which were very close to the motions I observed in Tracker. My model, I started out, I weighed the mass of my tin on a postal scale I have, and it was 620 grams exactly. At least that's what the scale said. So that's 0.620 kilograms, although the mass doesn't come into play for these calculations. I gave it the start position by the first plot point I recorded in Tracker, and I gave it the start velocity by taking from Tracker all of the displacement over x over the entire delta t, and that came out to be 0.54 meters per second. So I input my velocity as 0.54 in the x direction, positive. I just started time at 0, and I set my time steps to 0.0333, etc., which I can obtain easily by setting delta t equal to 0.1 divided by 3. I started the tracking at about 10 and 4 seconds and ended nearly 13 and a half seconds, so my total time is about 3.2 seconds. The calculations I had for my model, which I will go ahead and show you. Here's the model, and you'll see something looks a little wrong. It's moving to the right. Well, that's because the positive x direction for this model that I was given code for has it facing to the right. If I were to try and make it move to the left, my graph would be screwed up, and that wouldn't fit the model or anything like that, so I didn't do that. But it still models the motion exactly. Not exactly, but very well. You saw the graph that it output. I saved those points and plotted them against the Tracker points. You can see my points over here from Tracker, and my simulated points here. The red line is the simulated, and the blue kind of curved line is the data from Tracker. So my calculations in my model, I used the Newton's second law. I set net force equal to 0, and I went ahead and did all the verbose calculations. I calculated final velocity to set the can to at the end of the loop, and I found the new position the most verbose way using the calculus model, and it's just initial position plus initial time, or velocity times delta t, plus the net force divided by the mass of the can times delta t squared divided by 2, all divided by 2 on this term here. Of course, this is going to turn out to be 0, this term, because net F is 0. So that's not going to add anything to it. Constant velocity, and I set the new velocity right here, and so that's how my model works. Again, you can see here, it draws it rolling from the left to the right, just because the software already had a positive axis defined as going to the right. For the what-if questions, if I were to change my origin over here, just do that. If I were to change my origin here, then, well, the x values would change, maybe the y values would change, even though we didn't use those, and I could even rotate the origin so that it's going in the negative x direction. And that would change my model. I could rotate it so it's at 45 degrees, and it's actually a combination of x and y. That would also modify my model. But fnet is still 0 in all those cases. The 10 would still roll the same way, and the start, but the displacement would also still be the same. As for, is it possible to construct a free body diagram of the popcorn tin, showing all of the forces acting on it and showing that they do in fact cancel out? Yes, it would be possible to do that, because the only forces acting on the popcorn tin as it is rolling to the left are the gravitational force from the Earth, which cancels with the normal force coming out away from the Earth from my floor. They cancel each other so that popcorn tin doesn't do anything funky like sinking through my floor. As for friction, the popcorn tin is rolling down the hall. It's a very small surface area that's touching the floor. The friction is nearly negligible. I don't know how I would measure it. Hopefully I'll learn this semester. Because it's so slow, the air resistance is also pretty much negligible. So that's not contributing any forces there. So again, the only two forces are the normal force and the gravitational force from the Earth, which cancel out. And therefore, fnet is 0. Also, the observation and tracker starts well after my hands have left contact with the tin. You don't even see that happen off to the right of the video. And so I'm not applying any extra force. I'm not blowing on it with a bellows or anything like that. So those are the only forces left on it, and they cancel out so that fnet is 0. And that's why it has a constant